Many thanks for the introduction, Jamie. Hello, everybody. Thank you for attending my presentation today on working with powders, how comprehensive characterization can optimize your process. As you've just heard, I'm Tim Freeman, Managing Director at Freeman Technology. So by way of an introduction, powders are used extensively across a wide range of industries. They possess many valuable properties and benefits. However, they're also challenging materials with bulk flow properties that are difficult to predict, even within simple process operations. They change their behavior and performance depending on the environment. So changes in shear rate, stress conditions, storage duration, environmental humidity, equipment surface properties, etc., are all going to influence how the powder behaves. And a poor understanding of a powder's behavior in response to these variables can lead to production stoppages, production inefficiency, and poor quality or out of specification products. In order to achieve efficient manufacturing in high quality product, it's necessary to measure and understand powder behavior under all relevant process conditions. So let's look at some of the application areas. Pharmaceutical industry uses powders extensively within dry powder inhalers, where a formulated powder dose is delivered to the lung of the patient, and of course extensively within tablets and capsules, where many components are often blended together in order to form the dose, either in a compressed form and in an encapsulated form. Additive manufacturing is a relatively recent industrial sector, but growing in great interest and adoption across many areas. It's a process by which layers of powder are laid down and then sintered, and you can hopefully see in this video as it runs, in order to form a structure, and it provides many different benefits over to conventional manufacturing techniques, not least the fact you can form very intricate components. And you can see here as the video runs, a layer of typically 100 microns of fresh material is laid on top of the former surface, and then selectively those particles are fused or sintered to the substrate below by an energy source, typically in the form of a laser. And so flow properties are particularly critical here because you need a smooth surface in order to achieve good quality finished parts after the sintering step. Then we have powder coatings. It's an industry that's been used for many years, or that's employed powders for many years, and it benefits in contrast to liquid painting in the sense that there's fewer chemicals used in the process, and you get a very high integrity mechanical protection. The process is one by which powder is fluidized and then sprayed from a gun and attracted to an electrically charged or a static process, whereby the metal surface has a charge that attracts the particles, and hopefully uniform coating is achieved before that's then heated to form a permanent cover on that surface. And of course, cohesion, fluidization behavior are important attributes. If the material is too cohesive or agglomerated, then the surface finish may be compromised. And then within the ceramics and the metals industry, we have cold or hot isostatic pressing. Here, the particulate metal or ceramics are required to fill into a die, often of intricate shape, and the ability to fill that die efficiently is important, so that when it's compressed and then sintered, it forms the right mechanical geometries that were desired, and also the right mechanical integrity. And then, of course, within the food industry, there's a huge number of different materials, excuse me, many of which are naturally occurring materials, of course, and therefore include things like oils and fats, many different particle sizes and shapes. And the packaging in which they're distributed changes or is diverse in terms of its size and its shape. So the formulation is one aspect of the food processing industry, and then manufacturing and packaging is another challenging area. And then we have ceramics, toners, cements. So powders are used pretty extensively across a range of different application areas. So if we look at some traditional batch operations used in a powder processing environment, here we can see an example of a tablet manufacturing process. You might have raw materials stored within hoppers or silos. They are then dispensed into a mixer, materials then blended together. There may follow a granulation step, talk more about this later, whereby those previously free independent particles are now bound and agglomerated into a granule. That's often a wet granulation process, which of course then is followed by a drying process. That might then go through a granule or particle size reduction step before the addition of a lubricant. Finally, that pre-compression blend is added to the press or fed to the press, at which point that loose blend of powder is compressed to make the tablet that's the desired product. And often there's a coating process at the end. Similar configuration, but for continuous manufacturing, this is effectively a similar number of operations, but of course, because it's continuous, they are connected. So the ability to control the quality of the material leaving each of these operations in real time is even more emphasized in a continuous environment. But in principle, you can see you've got on the left-hand side, you've got a process flow, which is a wet granulation process. So you get dispensing through a dry mixer, continuous dry mixer. Then we have a continuous wet granulation process, which again, I'll talk about later, before that goes into in fact, a quasi-continuous type fluid bed dryer through a mill, lubricated, then onto the press, and tablets are manufactured. And this has been embraced by the pharmaceutical industry for probably the last 10 or so years commercially. Continuous manufacturing, of course, has been used in many other industries for a longer time. Within at least the pharmaceutical industry, there's also the dry granulation route, which is where you have, again, dispensing of your raw materials into a mixer, but they then go through a roll compactor or a dry granulation route before being lubricated and then tableted. And the key point is that the process operations here, the unit operations, will all have an influence over the properties of the material leaving each stage of the process, and ultimately the properties of the finished product. So whether it's a batch or a continuous process, a detailed understanding of the powder properties and those processes employed is important. The relationship between those material properties and the process conditions determines that quality of the finished product, the attributes of the finished product. So if we look at the tablet as an example of this process, you start with your raw material, but how it then is dispensed and discharged from the hopper, how it behaves in a feeder, through the blending process, through granulation, drying, milling, mixing, and so on, all compound right through to the final product. If you have a good understanding of each of these unit operations and can control the variables within them to give you the attributes that you want of your intermediate, then you have a good chance of making high quality product. If any one of those has an issue in terms of it's out of specification or it's a poorly controlled process, then the potential is that problem is propagated downstream into having a negative impact on the quality of the finished product. So if we look at some of those process variables, you can see here, for example, dispensing from a hopper, the hopper geometry and the material of construction is important. What it might lead to is issues to do with bridging or sporadic flow. In a granulation process, the amount of water that's added, the impeller speed if it's batch, the screw speed if it's continuous, the fill ratio, again, if it's a batch process, how long you're granulating for. Each of these variables associated with the process will have an impact on the quality or the attributes of the material coming out of that process and feed forward into the attributes of the finished product. And so you can see associated with each of these unit operations, there are a whole series of process parameters which will vary in terms of their influence and importance over the material properties. And so if we look at some of the problems that occur or some of the challenges in operating these operations, if you, for example, have a mixing process, you might find that actually you haven't achieved the uniformity. Maybe the particles suffer from mechanical attrition because the energy in the mixing process is too high and the particles break. There might be some electrostatic charging, changing how it behaves in a subsequent process. If you're talking about, for example, the granulation process, the granules may end up being too weak or indeed too strong. That definitely has an impact on the hardness of the tablet later on. And so on. Each one of these operations has a series of operation-specific challenges that need to be considered and understood in terms of their ramifications for the process and the product quality. So let's have a look at the constituent phases of the powder or of powders. These are multi-phase bulk materials made up of solids, which are the particles themselves, generally speaking, some liquid in the form often of water on the surface of the particle or within the particle, and gas, which is normally air, which exists between the particles. And the bulk powder behavior, in terms of its flow and compression and various other parameters I'll talk about later, is complex, and it will depend on how these three phases interact. But let's have a look in the first instance at particles, so the solid components. These are complex in their own right, and they're hugely variable. Traditionally, we've looked at things like particle size and distribution, and of course that is important. But there is a whole series of physical and chemical properties that need to be considered. Size and distribution is important, but shape, surface texture, surface area, particle density, whether they're cohesive or adhesive systems. They might be elastic or plastic materials. They might have a pore structure to them. They may be sensitive to electrostatic charge, sensitive to moisture, varying levels of hardness or amorphous content. So for a single particle, there's a whole series of physical and chemical attributes that could vary, and each of these has the potential to influence how that bulk powder behaves. For example, you could try and keep all of these consistent, but for example, change the shape of the particles, shape distribution, and it would have an impact on how that powder behaved. And what do I mean by powder behavior? Well, we know it's going to be a function of particle properties, size, shape, stiffness, porosity, all the things I've just listed, but also, as I said earlier, the environmental conditions to which the powder is exposed to. So the extent of consolidation. So does this material behave in the same way if it's consolidated under a consolidation stress? What happens if it's aerated or fluidized? It's going to behave in a different way. If you handle, store, or process the material at different humidity levels, certain powders will be sensitive to that and change their behavior in terms of flowability, compressibility, and so on. Also, the extent of shear stress and the extent of strain. So things like the shear stress levels imposed depending on the configuration of a blender, but also how long you run that blender for influences how much strain goes into the system. And then things like equipment surface properties. So what happens if you have a coated surface in the inside of a silo or a bin to influence the interaction with the powder? Does it facilitate better discharge or more consistent behavior? And there's no mathematical way of predicting this behavior from primary properties. You can see that if there were just 12 variables, each with just 4 permutations, you'd get 16 million combinations. And of course, there's many more than 4 permutations for each of those parameters like size and shape. So it's an infinite combination mathematically, and that's a simplification of why we don't have a fundamental approach of predicting powder behavior from knowledge of the particles and the stress conditions alone. And you can see in this animation an illustration really of how these particles interact and behave under different stress conditions. If you discharge a powder under gravity, the powder bed will naturally dilate and air gets into the bed. The density reduces, and actually the flowability, the ease with which it discharges the second time, is much easier. It becomes much more liquid. But if you take that same collection of particles and you vibrate or you consolidate it, the gas, that component, that phase is extruded from the powder bed, and you get a totally different interaction between those particles. So depending on the stress conditions, you can have a fluid-like response like the one in the center here, an intermediate type flow, or no flow at all. And the interesting thing about that is that it's the same powder can flow like a liquid at low stress, or it's behave like a single solid entity if it's consolidated. The particles have got the same physical properties, so you haven't necessarily changed anything about that, but depending on the imposed stress conditions, which of course vary significantly during any process environment, you will observe different performances of the powder. Some materials are tolerant to these extremes, others become problematic, and a consequence of that is that you have process interruption or quality issues. So I'm briefly going to introduce the FT4 Powder Rheometer. This is the flagship product from Freeman Technology that we have been known for a number of years. I'm going to introduce it because some of the data that it derives, it measures, is used in some of the case studies in the latter half of this presentation. And the principle of operation is that we have a blade and a powder sample, and the blade is inserted in the instrument, as you can hopefully see here in this image. And then you have a powder sample contained within a glass vessel, typical sample size from 10 milliliters to 160 milliliters, depending on your configuration. And so we conceived of something we call dynamic testing. This is when the powder rheometer measures the resistance that the powder exerts on the blade as that blade forces its way through the sample down a prescribed path. So we define effectively the helical path angle and the speed or the shear rate that we want to impose at the blade. And that resistance is expressed as a flow energy, which is calculated directly from the measurements of the torque, so the rotational resistance, difficulty with which the system resists the rotation, and also the axial force. So it's simple Newtonian mechanics of work done, impose a particular flow pattern and measure the powder's response to it, the resistance imposed. And we call that dynamic testing. We can actually do that whilst also introducing air. So with the addition of an aeration control unit, which you can see here in this right-hand image, and an aeration base, which goes into the bottom of the powder vessel, we can introduce air from 0 to maximum requirement in order to aerate or even fluidize the sample. And the purpose of that is to assess how the flowability changes as a function of aeration. I'll talk in some more detail later about that. Alternatively, you can change the blade for a piston, a vented piston, which allows air to escape through the surface. And we can measure the air pressure differential across that powder bed for a given consolidation stress and for a given gas velocity. And that gives us a measurement of the permeability of the powder. We can use that same piston, but without an air supply, to simply measure compressibility, so changes in density as a function of applied stress. And we also have what we call a shear cell accessory. I'm sure many of you are familiar with these types of methods, but simply it's a quasi-static measurement in contrast to the dynamic measurement. So this is about the onset of flow at very low shear rates, and it's a measurement under consolidation or consolidated conditions. So here, there's an applied normal stress or force, and then whilst that's being controlled, rotation occurs and the powder slowly begins to shear, resulting in an incipient failure or the yield point of the powder bed. And by plotting the relationship between shear stress and normal stress, you can derive the yield loci and various other parameters that relate to flow behavior of the material, particularly good for understanding behavior in bins and silos. If you change the hardware for a wall friction accessory, you can see in these bottom right images here, same methodology, except this time you're measuring the powder against that wall coupon, and you would obviously select something that would be representative of the process equipment so that you can understand what levels of friction or resistance to shearing exist between the material within the equipment and the equipment wall itself. And that can lead to justification or otherwise for example, changing the surface properties inside silos and hoppers. So methodologies with the FT4 are quite diverse. We have what we call bulk characteristics such as density, compressibility, and permeability. We have a dynamic flow, which is allowing us to look at how powders behave in a confined state. So being forced to flow, a bit like in a feed frame of a tablet press, the paddles are forcing the material around, and that's a basic flowability energy measurement, as we would call it. We assess how the flow energy changes when you aerate the material, when you consolidate it, when you impose flow at different flow rate or strain rate conditions. And we also quantify something called the unconfined flow. This is a very important difference to the confined flow regime. This is about how material would flow without being imposed upon by an external stress. So this is really about whether something would flow under gravity, and it's dependent very much on the mechanical interlocking between the particles. Then we have shear methodologies, so the shear cell and the wall friction I just talked about. And then finally, what we would call process type investigation. So propensity to segregate, particle attrition, looking at sensitivity to caking under different effects of temperature and humidity and duration. We can assess the effect of electrostatic charge within the material in terms of how the flowability changes. Same thing for moisture. And we can look at the effect of propensity to agglomerate, for example. So it really is a versatile instrument that allows you to investigate many different attributes of materials, or powders, and that's essential, as I'll show you in the second half of this presentation, where we're starting to look at a variety of case studies. In this first one, we're looking at wet granulation and tablet manufacture. So pharmaceutically focused, but nevertheless relevant unit operations across many industries, and the concept of assessing the process variables and understanding their impact on the material that you're manufacturing is consistent, whether you are employing wet granulation and tableting materials or other unit operations. For those that are not that familiar with wet granulation, this is a process that converts fine powders, typically with poorer flow properties, into large granules, and the benefit is that you get improved flow, you get a reduction in reduced segregation potential, that leads to better content uniformity, improved compression properties, and reduced dusting. And granulation via this technique is a high shear process. It can be a batch or a continuous process. You can see a typical, very simple sketch of the batch process on the top right here. You have an impeller on the bottom of the granulator bowl. You fill your blend and your measured components into the bowl. You have a high-speed chopper, and what's not shown actually is the addition of water as a binder. And this process then continues to make a batch wet granulation. In contrast to what I'm going to talk about shortly in the rest of this application, a continuous process whereby powder is fed into this hopper. You have a twin screw that kneads and conveys the material through the process as water is added, and out the other end comes a granule with certain properties depending on your configuration. But in both cases, liquid is introduced whilst the powder is being sheared. And your variables are process specific, but of course the amount of water you add is something you can control and is important. The granulation time, duration of granulation within batch processes, the rate at which water is added, the screw speed for the continuous setup, the powder feed rate into that screw, and for batch, the impeller and the chopper speed. And so what we did in this experimental program, which was in fact a collaboration with GEA Pharma Systems, was to investigate the change in material properties, both of the wet and the dry granules as intermediates, as a function of changes in the formulation and also the process configuration. So we're interested in the attributes of the granules that come out of the granulator in the wet form and also after the fluid bed dryer. But that's all very interesting. That's an in-process kind of intermediate type qualification or characterization of the material. What we really want to do is relate these to attributes of the finished product, the tablet itself, which of course is the final entity that the manufacturer is trying to produce with having met the appropriate quality attributes. And so here you can see the Consigma 1. It's a high shear wet granulator and drying system from GEA, and it's a highly versatile bit of equipment because it allows you to scope process settings very quickly. And what you have in principle is a loss in weight feeder and a hopper here that contains your pre-blend. That is metered into the screw. Sorry, the image is quite small here. This rectangular object on the top here is the twin screw granulator element itself. There is a peristaltic pump which feeds in water that goes in towards the start of the screw, so you have a dry powder blend fed into the screw, water is added, and mechanical shear is imposed as it goes through the screw, as it's conveyed through the screw, and out of the screw into the dryer comes your wet granules, which are then obviously dried for a specific configuration or specific time. And those process variables that you can manipulate, as I mentioned, are the water content, the screw speed, the powder feed rate, because that influences the fill ratio within the barrel, and the barrel temperature. And then within the dryer, obviously you can change things like the drying time, your air velocity, your air temperature, etc. And each of these has the potential to change the attributes of your wet and dry granules respectively. So in terms of the experimental plan we had with the collaboration we did with GEA, we took two formulations, pretty straightforward. One was an acetaminophen, an APAP or paracetamol with a 90% drug loading. The other one was dicalcium phosphate, again, high drug loading. We wanted to change process variables by varying the amount of water required to provide granules that had different properties, of course, from undergranulated to overgranulated, and that was determined visually. We wanted to manipulate the screw speeds, so we chose 3 different screw speeds of 450, 600, and 750 RPM, and we wanted to change the feed rate of the dry powder feeder into the screw itself, and we deviated from the standard 25 kilograms per hour to a 20 and a 15. So again, we used dynamic characterization. This is the FT4 measuring the resistance of the powder, or in this case, the granules that they exert on the blade as it forces its way through the sewing pole. And we know that that resistance is expressed as a flow energy, so the calculated resistance measured directly from that force and the torque. So what you can see in this data set is the flow energy measured on the y-axis, and then you have on the x-axis the water content. So this is changes in flow properties of the wet granules, so directly from the granulator screw before it goes into the dryer, as a function of water content and screw speed. This is for the acetaminophen, and in all cases you can see that as you add more water, you end up with a higher basic flowability energy, so that represents denser, bigger, stronger granules. And interestingly, quite a significant effect on screw speed. You can see the lowest screw speed at 450 RPM gives us this blue data set, and therefore substantially stronger and bigger granules at these lower shear rates, which is perhaps counterintuitive, but it allows more time for the particles to shear and for the fluids to disseminate or to distribute through the sample, and for larger and stronger granules to form. What you see on this data set is, again, for wet granules, but this time for the dicalcium phosphate formulation, showing how granules of similar properties can be manufactured using different conditions. So the red trace shows the DCP all at 600 RPM screw speed and all at 15% water addition, but we're changing the feed rate of the blend into the screw. So we're modulating the percentage water to match the feed rate. But you can see that the water addition between the 15, 20, and 25 is quite a significant effect. And what you can see here, this example at 20 kilograms per hour with a 15% water addition has the same attributes as that at 20% water with a higher feed rate. So by manipulating your process parameters, you can identify how they influence the attributes of the material that are coming out of that process step. And of course, that gives you a substantial step towards being able to employ a quality by design approach of identifying critical process parameters and using those to design in attributes that you desire in your finished product. And so we took this study further with one of the APIs, and we designed 4 conditions or 4 configurations. You can see here in this table on the left-hand side, and they are all variables associated with the wet granulation process. We had fundamentally 2 different speeds, 450 and 750 were chosen, and you can see on the right-hand column the moisture content that we chose as our set points. We've got 2 relatively low moisture contents, 8% and 11%, and we've got 2 higher ones at 20%. And so what we did is we made granules following these process parameter set points, and we measured their attributes at each stage through the process. In the first instance, we've got granules directly from the granulator, so they're in the wet phase, and you can see typically there's a lot of data on this screen, so I apologize. I'll try and explain the pertinent points. The lower flow energies here, you can see around the 2000 millijoule mark, are derived from or are measured from the condition 1 and 2, where you have a low water content within your formulation. And then you have a substantial jump in flow energies up to 3,200, 3,300 when you go to the higher water content. So perhaps not surprisingly, if we're contrasting just water content changes, the more water you add, the bigger, stronger the granules, the higher the wet mass basic flowability energy. If you then take each of those candidates and put them through the dryer, you can now see that you have a change in flow properties. The lower moisture content samples actually reduced in flow energy, probably as a process of some small amounts of attrition and rounding of those granules, which are not so robust, not so hard. The opposite is true for the denser granules, which probably preserve their structure, but in fact become quite stiff systems as the moisture is removed. And then as we go through the milling process, you change the flow properties, of course, you're changing the granules shape and size. And then into the lubrication step, we're adding magnesium stearate here. Again, you change the flow properties of the material. So we can track the attributes of those different conditions right through the manufacturing stages. And that's all very interesting, but as I said at the start, one of the aspirations was to try and evaluate how those changes in granulation parameters translate through to variations in finished product attributes. And so we used another GEA system, this time a Module S tablet press, which is a hugely functional component piece of equipment, but obviously can be configured in a simple kind of non-automated mode, where we change or we restrict the automation of it and just set the punch positions and the stresses that it's going to impose on the tableting process. And we made tablets from each of those 4 conditions. And what we can see, again, a graph with quite a lot of data, so I'll take some time here. It plots the relationship between the tablet hardness. So we simply made tablets in the hundreds from each of these 4 conditions. And it plots that hardness data against, on the x-axis, that basic flowability energy, that flow property data from each of the conditions. The wet mass is this magenta line, dried granules, and then the milled and the lubricated granules here. That's these are less differentiating down at this milled and lubricated end, but you can see here very strong and discerning differences between the granule attributes when they're wet, and particularly when they're dry, and tablet hardness. And what that allows you to do as a process engineer, as a formulation scientist, is to assess that intermediate part way through the process. If you have a flow energy of, let's say, 3,000 millijoules, you know you're going to end up with tablets at around 9 kilopascals. And so you can manipulate this within your process development exercise and say, okay, I want wet granules with, let's say your target hardness is 10 kilopascals. I want wet granules with a basic flow energy of 2,800 millijoules. Anything above that, you know you're going to end up with tablets that are going to be too hard, and if they undergo the same process compression activity. Anything below that, you end up with tablets that are too weak or too soft. And so it's a tool that allows you to link intermediate granule attributes to the final product critical quality attributes. This next case study, I'm going to look at statistical analysis of screw feeding. Screw feeders are, of course, employed across a wide range of industries as a way of controlling the flow of powder from a hopper into a downstream process, for example. They involve one or more rotating augers in an enclosed space, driving powder forwards following the Archimedes screw principle. I'm sure you're all familiar with this. Powder properties will affect the performance within the feeder. If you've got a powder that's poorly matched to the application, it can be problematic in terms of low and or sporadic feed rates. It can present high torques on the screw, and you may find you get accumulation of the powder at the wall of the feeder. So, however, if feeder performance can be estimated from measurements of powder properties, this enhances the efficiency of the process, of course. So what we did in this study was took 5 powders and we evaluated them with the FT4. In fact, I say we did. This was a collaboration with Granulation AG, who are a feeder blender manufacturer based in Switzerland, who use an FT4 for powder characterization. And they extensively characterized these 5 materials: calcium hydroxide, maltodextrin, milk protein, cellulose, and a calcium citrate. And here you can see the 2 feeders that we used in this particular study, both Granulation feeders. One is a single screw and the other is a double screw design. So the GLD is the single screw design, GZD, the double screw. And again, these are sophisticated operations or units. However, we can configure them to operate in just a volumetric feed mode. So we just set effectively the screw speed to rotate at a fixed rate for a given duration. And in that way, it can operate in a volumetric mode of operation. And the intention was to try and find a correlation between the measured material flow and bulk properties and the performance in the screw feeder, allowing them to predict the process behavior from measurements of the powder properties. And so they ran dynamic flow property tests, they ran shear tests, wall friction, density, permeability, and compressibility on all 5 materials, typically resulting in RSDs of less than 5%. The volumetric feed rate in litres per hour was measured, or calculated, I should say, from the measured mass flow rate in kilograms per hour and a knowledge of the measured bulk density. So they simply used a balance to record how much mass was being accumulated per hour effectively, and from that we could back out the volumetric displacement over that duration based on the knowledge of the density. We used multiple linear regression on the results to generate a relationship between the FT4 parameters and the feed rate. And then we tested that, of course, by calculating feed rate for 2 new powders from measured FT4 parameters and then measuring their actual feed rates in the hopper. So we wanted to challenge that model. I'm sure you're familiar with multiple linear regression, but very briefly, this derives a model that predicts an output Y for given values of X1, X2, etc. And our squared value represents the quality of the fit of that model. And in this case, each X parameter represents the value of an FT4 measurement, with the Y parameter representing the feed rate. We used a relevance parameter P to indicate the likelihood of that parameter's contribution to the relationship. And so the smaller that value, the more likely the parameter is to be relevant. Anything greater than 0.1 we considered to be insignificant. So parameters that gave us p-values of less than 0.1 were considered in the model. So here we have a whole series of measured properties for the 5 materials, starting left-hand side here, calcium hydroxide down to calcium citrate. You've got dynamic flow properties from the FT4, so the confined and unconfined dynamic flowability energies, the sensitivity to being measured or the stability of the sample, the strain rate or the flow rate sensitivity is the flow rate index, the sensitivity of the material to aeration and also consolidation. Then we quantified bulk and tap densities. We quantified and measured the compressibility and the pressure drop. And then with the shear testing, we measured unconfined yield strength and major principal stress. From that, we could calculate and derive flow functions, cohesions, and angle of wall friction. And then finally, we did a angle of internal friction. And then with the wall friction test, we could measure the wall friction angle. And so all of these parameters, the majority of this table are from measurements from the FT4. And at this point, we weren't sure which parameters were going to be relevant to the data in this right-hand side, which is the feeder parameters. That is the volumetric feed rate in the single screw in liters per hour. So again, we've measured the mass, we've accumulated in an hour. We know the density, so we know the efficiency of the displacement of the screw based on that volumetric calculation. And you can see, so during that hour, you've got the same number of revolutions of the screw in the feeder, but you've managed to displace 50 litres for the calcium citrate, in contrast to 185 litres of material for the same number of rotations of the screw. So clearly the performance of the screw feeder for the calcium citrate is nothing like as efficient as it is for the calcium hydroxide because of the inferior properties of that calcium citrate. And so we did the MLR regression analysis. That found a pretty robust R squared of 0.95 relationship between feed rate and the strain rate, or the flowability, the flow rate index properties, and the unconfined flow behavior, the specific energy. And really, they were considered the only two that were needed in order to predict with pretty decent accuracy the expected volumetric feed rate. And so if we look at that as a function of predicted versus calculated, you can see for the 5 materials the match is pretty good. And you've got your the highest volumetric displacement for the calcium hydroxide on the left hand side here, with a almost overlapping predicted and actual, right down to the sort of the 50 to 60 litres per hour as demonstrated by that calcium citrate. So pretty robust model. But of course, we built that based on the parameters we've characterized here. So what we wanted to do was take 2 new materials that weren't part of that model, put them into the equation, and you can see our R squared is still 0.91, so 91%. Cement and lactose, very different materials to each other and to the rest of the set from which the model was built, and you can see a reasonably decent correlation between the predicted and the actual observed feed rates. When we did the same thing for the twin screw, we of course had the same material properties as measured by the FT4, but you had very different volumetric displacements because of the scale and the configuration. That was intentionally much lower throughputs, more precise process typically, but again, a kind of a 3.5 to 1 type performance. And interestingly, in this case, it was the aeration characteristic that proved to be most relevant. And here we can see again an 83% R squared value, suggesting that this was a robust prediction. When we looked at the actual versus predicted, again, pretty good with residuals plus or minus 5 or 6 litres per minute, so sort of 10-15%. When we put in the subsequent cement and lactose samples, again, we observed reasonable accuracy with our predicted versus the actual observed retrospectively. And what that shows is that we needed, or that the behavior of the materials within the 2 different screw designs is dependent on different attributes of the material. And that's probably not surprising when we consider the scales are different. You have twin screws versus single screws and so on. And it's that complexity of the unit operations that makes it currently impossible to be able to predict from a fundamental basis what kind of material attributes are going to make a process work in the most efficient, consistent way. And so for my final case study in this presentation, I'm just going to introduce something that's relevant to many different industries, the pharmaceutical industry as well, but many companies in battery and cosmetics and metals and ceramics use dye filling processes. Here you can see a design that's such that it's a shoe filling approach. So you have powder in a hopper that's dispensed within a feeder. The feeder moves across the dye, generally gravity fill. In this case, there's an initial compression, maybe a compaction, and then an ejection step, and you have the finished form. And so for good filling performance, we want uniform fill, low porosity. You want a consistent fill weight. You don't want lots of air gaps in there. If you have inconsistency, non-uniform filling, you have high porosity, and the ramifications are variation in part weight, but probably more importantly, structure of the component. So the mechanical integrity is compromised. And so the question is, what properties restrict filling of the dye? Well, I'm going to propose 3 important characteristics that are going to influence the filling performance, and then show you some data that hopefully supports that proposition. High cohesion, so the tensile cohesive forces that exist between particles are going to influence whether they flow uniformly under gravity or remain as agglomerates and inconsistent in terms of their flow. high mechanical friction and interlocking. We're going to use a particular test to explore the influence of that phenomena. And we're also going to assess the permeability of the powder bed, because for these particles to flow into a die, the air has to flow out and therefore backflow through the particles. And as a consequence, permeability is an important part of the process. So we measure cohesion, in my opinion, the most direct way through the aeration test. So what you have here is the flow energy of the sample, and we measure it as you go from 0 gas velocity to an increasing level of aeration. And so for non-cohesive powders, where the cohesive or the tensile forces that hold particles together are weak, the powder is able to fluidize or fully aerate as that gas permeates through the powder bed and it pushes the particles apart. They're not stuck together through high electrostatics or high cohesive interparticulate forces. And as a consequence of that full aeration or fluidization process, the resistance to flow reduces to an asymptotic and very low level. Of course, for cohesive powders, you also get a reduction in flow energy, but you're not breaking down individual particle bonds. They may get separation between agglomerates, but those cohesive structures remain, and the change in flow properties is much less. It still becomes asymptotic. There's a steady state equilibrium, but basically what we're looking at here is a low value of aerated energy means it's a low cohesion system. It can become fluidized or aerated. A higher value of aeration means that you've got a significant amount of, a high value of aerated energy means you've got a significant amount of cohesion within the bed. We measure with our unconfined flow, or the specific energy test, the upward measurement, and so this is the resistance of the powder bed to being lifted and to flowing just under gravity. It's very good at looking at the effects of interlocking and friction. And then we use the permeability configuration to measure the pressure drop through the bed, so imposing a consolidation stress on the x-axis, a gas velocity which you can set to any desired amount or go through a range, and we measure, whilst confining that powder bed under a consolidation stress, the air pressure across that powder bed. So a powder that's got low permeability would mean you would have a high air pressure differential across the base or across the bed, because it's difficult for that air to percolate through the particles, between the particles, and out into the atmospheric relative pressure. So in this experiment, very simple, we wanted to design a simple experimental setup that we could build in our own lab. We had a shoe, which was a glass vessel. We could fill that to a specific volume, and we could prepare it by conditioning the sample first, so standardizing the density, and then it would move a single pass from right to left across the top of a die, which was a known volume, and we could do that at a specific controlled speed. And so we can establish how effective the material was flowing into the die based on the speed at which the shoe moved relative to the die, and also the material properties. And we took 4 different candidate materials, 2 glass beads, you can see here of generally spherical morphology, different particle sizes with a D50 of 174 and 68. We had a relatively large particle size granular aluminium powder, but an irregular morphology, as you can see in the image, and then a tungsten powder, which is a D50 of about 4 microns and angular in nature. And so we ran these 4 materials through the same setup with different shoe speeds, and we assessed what we call the filling ratio. So the amount of material that actually transferred from the shoe to the die on that single pass as a function of shoe speed. And you can see the x-axis here represents that shoe velocity relative to the die, 50 up to 230 millimeters per second. And you can see this fill ratio, the y-axis, 1.0 represents 100% full, and of course we can measure the mass of the sample. We know the density after the pass, so we can accurately define or verify how much material was deposited in the die after the shoe passed across the top for a given speed. And you can see the tungsten, this blue data set here, is actually reasonable at filling at particularly the lowest speed at 50 millimeters per second. It fills to about 95%, but very quickly reduces in terms of its filling efficiency as the shoe speed increases to 150 and then 230. In contrast, you've got the large glass beads. Even at 150 millimeters per second, it's pretty much filling to 100%, reducing only to about 82% at the highest speed. So what we can do is we can use this process performance, let's say this fill ratio at 230 millimeters per second, to quantify how these material properties influence behavior within the shoe and dye filling system. So if we have a look at that filling ratio plotted for the 4 different materials, we've got 82% for the large glass beads, and this is again at that highest shoe speed, 230 millimeters per second, down to about 15% for the tungsten. So let's have a look at some of the material properties. This is the aeration data. And what we can see here is that 3 of these materials result in a fluidized state. So that flow energy of the aeration test drops down to effectively 0, which tells you it fluidizes. The reason it requires different minimum fluidization velocities is because the particles are different size and they're different densities. But the fact that they fluidize means that the powder bed has become fully dilated and the measured resistance is effectively 0. In contrast, the tungsten, which is much more cohesive, becomes asymptotic at about 300 or plateaus at about 300, which is a significant level of cohesion. So we can see 3 of these materials were non-cohesive materials. 1 was a particularly cohesive material in the case of the tungsten. And that's pretty robust. The tungsten is the worst performer, but there is significant difference in process performance between these 3 materials with the same levels of minimal or 0 cohesion. So let's have a look at the mechanical locking, the influence of shape. You can see that the spherical particles, the glass particles, are the lowest specific energy, whereas the angular and irregular shapes are the much higher specific energy. So that kind of makes sense. What's a bit strange here is that the best flowability material is the small glass beads. It's got the lowest specific energy, so the lowest mechanical locking. It fluidizes, and yet it only fills to 40%. Whereas the large glass beads, it's not bad in terms of its specific energy. It's a value of about 3.5, which is a moderate, but it's higher value, of course, than the smaller beads, and yet it fills to 82%. And the question is, why is that? You might expect, for example, this interlocking parameter to be a bit lower to support the fact that the material behaved well in the process. So what we're saying from that data is that for 3 materials we had low cohesion, for 1 material we had high cohesion, as defined by the aeration characteristics. From the specific energy, we can see that we've got the lowest mechanical interlocking for the small glass beads and the highest for the tungsten. And yet, as I said a moment ago, the flow properties of this material seem to be the best, but the process ranking is not the best. And in fact, it performs half as well as the large glass beads. And the question is, what's the rationale for that? And if we look at that pressure drop, the permeability data shows that the small glass beads has a pressure drop, a measurement of 5.2 millibars compared to 0.8, telling us it's about 6 times more difficult to get air to backflow through that material during the filling process. So whilst it flows into the vessel very effectively, or whilst it has very good flow properties, it can't flow into the vessel as easily as the large glass beads because the permeability is restricting that airflow. And so it illustrates again how you need multiple attributes within a specific range in order to achieve efficient process performance. And in this case, for filling, we need low cohesion, so a low aerated energy data, moderate to low mechanical locking, which is specific energy data, and a high permeability, so a low pressure drop. And that gives you your process ranking. Anything outside of these spaces is going to start giving you filling performance that's sub 80%. And sadly, that's as complex as that is the necessary approach in order to rationalize and to predict process performance. The correlation between measured material properties in a good experimental plan and very importantly, process relevant flow properties and what you observe within that experiment itself or that process itself. So this is bringing me to the end of the presentation. We do have experience in lots of different powder processing environments, including dye and capsule filling, tablet compression, hopper flow, granulation endpoint and scale up. I've talked a little bit about today. We're working increasingly with additive manufacturing sectors, looking at spreadability and part uniformity, optimization and selection of flow additives, the effect of humidity on material behavior, sensitivity to electrostatic charge, blending and mixing operations, feeding I've talked about, segregation propensity, looking at things like particle attrition. How does that change when you impose a certain amount of energy or stress into the system? Do the particles change their attributes, and therefore does that influence the flowability of the material? Dry powder inhaler applications, caking, milling, conveying, wall friction and adhesion, hopper design, which is an integral part of our data analysis software and capabilities with shear cell, wall friction and density measurements, and then industry specific tests such as compact hardness and payoff for the cosmetics industry. So a whole range of application areas related to powder characterization and understanding process behavior and product quality issues and how we can relate those two things. So in conclusion, powders are complex materials. Single number characterization or even single techniques not going to thoroughly describe powder behavior in every process. It's essential to have a multivariate approach and to measure the right characteristics for that particular process. Achieving high quality of finished product requires an understanding how those material properties and the process variables influence the attributes of the finished product. It's essential to identify and measure the most relevant material properties in regard to that in-process performance and also your critical quality attributes, the finished product quality. Now, with FT4 and other techniques, modern instrumentation allows us to emulate a range of process conditions, and that means that a database of process-relevant powder properties can be established. The hard-earned experience that exists within production and troubleshooting and pragmatism and just the know-how that exists across many production and industrial environments can be quantified now, because there are always products that are difficult to manufacture, those that are okay and some that are really easy. If we can start to put a broad range of characterization or characteristics measurements into a database that describe how they behave in process, you can start to rationalize why these materials are good and some are more problematic. And of course, that correlation can then be fed back into R&D. So when you're designing new products, you're looking for attributes that you know are desirable and are effective in your existing processes. That means that predicting performance can be achieved with some confidence. Batch-to-batch variability can be investigated and understood and hopefully minimized. And productivity and product quality can be systematically enhanced through the application of the most appropriate measurements. So before I conclude, just like to highlight the breadth of application and technical capability we have within the Micromeritics family and portfolio. Freeman Technology is part of that group, as many of you will know. And across the range there, we have catalyst characterization and process development. We obviously have powder characterization, some very competent measurements within surface area and porosity, particle sizing and shape, and of course density measurements. And we also have in various locations around the world, US, Europe and China, the Particle Testing Authority, which is a contract lab function which gives access to people who don't necessarily have these technologies in-house but want to run samples through these instruments. So quite a broad range of capabilities within the group. So with that, thank you very much for attending the presentation today. If you would like to contact us or have any questions, hopefully we'll have a few minutes in a second. But otherwise, there's more information on freemantech.co.uk or micromeritics.com. And with that, I'd like to hand over back to Jamie to see if there's any questions. Thank you.